Hello everyone, my name is Riccardo Reali. I am a PhD student from the University of Florence, and I'm going to present a research paper titled Compositional Evaluation of Stochastic Workflows for Response Time Analysis of Composite Web Services. Our paper aims to perform quantitative evaluation of complex workflows, where a complex workflow is a structure that presents a high number of concurrent transitions that are generally distributed over bounded supports. Complexity breaks the efficiency of known techniques, and to perform evaluation of these models, it is necessary to apply a compositional approach that decomposes workflows into reduced blocks that can be efficiently analyzed in isolation and recombines results to form the cumulative distribution function of the completion time of the original workflow. Results will be evaluated in terms of accuracy and performance for the case of a composite web service, but it is worth to notice that a class of considered workflows can be used in many different contexts. Our work is implemented as a tool chain, here represented as a data flow diagram consisting of three different segments. The first aims to derive workflow distributions by approximation of histograms generated by logged data of real web services. The second aims to derive the used workflow by defining its topology as a stochastic time Petri net and assigning computed approximations to model transitions. And the third applies our compositional method by identifying blocks of a workflow, analyzing them in isolation, and recombining results. We said that one of the paper aims is to perform quantitative evaluation over complex workflows. Complex workflow means a structure that presents a high number of concurrent transitions, but also means that we consider durations that are generally distributed over bounded supports. This feature allows a higher expressivity, but also leads model to increase the concurrency degree between transitions and to have a lack of regenerative states, disabling the application of efficient analysis techniques. We model such workflows as stochastic time Petri nets, composed only by generally distributed and immediate transitions. We consider workflows that present five kinds of patterns. The first is the sequence pattern, which is used to represent a sequence of activities. Then we have the end split and the end join patterns, which are used to represent concurrent flows of activities. And finally, we have the XOR split and the XOR join patterns to represent alternative flows of activities for which only one flow can be active at a time. Note that such definition enables the nesting of patterns, producing a well-nested structure. Distributions assigned to model transitions are obtained by approximation of histograms. We created histograms by collecting the response time of many real web services taken from the WS-DREAM dataset, which is widely referred to as a benchmark in the literature. Before collecting samples, we operated a regularization by applying the Takis rule. This rule is widely used in the literature and consists in discarding the outliers of a dataset. And this is a necessary passage because otherwise the calculated histograms would appear stiff and ineffective at capturing the true shape of the distribution of data. We then collect the undropped samples into histograms. We approximate histograms with bilateral truncated exponential distribution, for which we obtain parameters lambda and delta by fitting mean value and standard deviation of histogram, while parameter b is the upper bound of the regularized histogram support. This is an example that shows the approximation distribution over a regularized histogram generated by a web service from the WS-DREAM dataset. And as you can see, the approximation is quite accurate, showing the potential of this class of distribution in approximating histograms. Our compositional approach is based on four operations. The first one is the decomposition of a workflow. Decomposition is performed whenever our workflow complexity is too high, and it is obtained according to the workflow topology. When isolated, identified blocks are independent workflows, which are in turn subjected to complexity evaluation and possibly to further decomposition. Then we have workflow complexity evaluation, which is done by applying some heuristics on the state class graph output by non-deterministic analysis of the workflow. Another operation is the analysis step, in which every identified block is analyzed in isolation through regenerative transient analysis based on stochastic state classes. And then the last operation consists in combining intermediate results numerically. Assuming that a workflow is too complex, we identify two possible strategies to decompose it. The first one is called split strategy, since it uses n-split transitions to separate the workflow into three blocks. One is the block that precedes the n-split transition, and the others are the two that succeed the n-split transition. The second one is called join strategy, since it uses n-join transitions to find points where the model can be decomposed into two sequential blocks. Complexity of a workflow is evaluated through the non-deterministic analysis that computes the state class graph of a workflow. A state class is a tuple consisting of two elements, the marking of the state and the dBm zone that represents the time-joint domain of that class. Non-deterministic analysis is also able to identify regenerative states that are those states where no enabled transition persists, making the Markov condition valid again. The state class graph allows to represent the concurrent behaviors of the workflow, and this enables some heuristic through which evaluating its complexity. In particular, we use two heuristics based on two arbitrary thresholds, D and E, for which we consider a workflow too complex whenever the maximum concurrency degree or the maximum consecutive transition firings were greater than the related thresholds. Workflows we handle subsume Markov regenerative processes that are processes for which a regeneration will be eventually reached with probability 1. For this class of processes, the probability of reaching a certain state j at time t, starting from an initial state I, can be computed as the solution of a system of integral equations of Volterra that can be solved numerically, assuming that we are able to compute the global kernel G and the local kernel L. Since the solution to this method is computed numerically, a certain amount of error will be introduced in the result, depending on how fine the time tick between consecutive samples is. Kernels are evaluated through the method of stochastic state classes. A stochastic state class is one of the state classes computed with non-deterministic analysis, which is here associated with a probability measure. A stochastic state class encodes a sequence of transition firings and the probability distribution of that sequence. And this information can be used to compute the global and the local kernels. In principle, straight enumeration of stochastic state classes enables quantitative evaluation of workflows, but as soon as the state class space grows in dimensions, enumeration of successive state classes grows in complexity. A great feature of Markov regenerative processes is that the state class enumeration can be limited to the state classes before a regeneration and repeated for all the regenerative states, cutting down complexity. And this is motivated by the fact that whenever a regeneration occurs, the future does not depend on the past anymore. And this is the reason why workflows are decomposed. When blocks are isolated from the rest of the workflow, many regenerations may appear in the block, so that it is possible to exploit them in the analysis technique. Since analysis outputs results in numerical form, after the decomposition, intermediate results are recombined numerically according to the initial net topology. And since we consider well-nested structures, the only allowed operations are sequence and an XOR of the intermediate results. We experimented our approach over a workflow that has been obtained as an extension of a travel agency composite web service, consisting of 21 web services. Experimentation has been repeated for 1,000 times for different time tick values. For every setup, activity distributions have been computed as bilateral truncated exponential distributions that approximate histograms drawn randomly from a population of 100 histograms. Results have been compared with a ground truth obtained as a 50,000 runs simulation. Accuracy has been evaluated using Jensen-Shannon divergence, which allows to measure the similarity between two probability distributions. Jensen-Shannon divergence is a symmetrical measure which is defined through the Kullback-Leibler divergence, and here it is used to evaluate the error between the workflow completion time computed by our approach and the workflow completion time computed by simulation, which is our ground truth. The table shows the average of the Jensen-Shannon values computed for all the experimentation setups. Each row refers to different time t cases, which are ordered from the coarser to the finer. The table and the graph prove the accuracy of our method since we scored very low values of Jensen-Shannon divergence in all the time t cases. Divergent values are proportional to the time ticks, and we obtain better results reducing the time tick, as shown in the finer time tick case, where we score a value equals to 0.0028. But this was an expected result, since accuracy suffers the discretization introduced by the system of equations of Volterra. And the bigger is the step, the lower is the accuracy. Regarding to performances, it is possible to see that, in average, the value of computation times is inversely proportional to the time tick of the analysis. But this was expected too, since numerical calculations must be executed for more points. However, comparing analysis and simulation in the case of the finer time tick, we can observe that even if this is the worst case time analysis, simulation requires almost 15 times than the analysis. And this highlights the efficiency of our compositional method, which can provide very accurate results in a very short time. The paper is associated with an artifact that implements the toolchain that we have presented. The artifact received ACM badges for functionality and availability, and the toolchain is mainly implemented in Java, and it exploits the serial library from the Auris tool to build the experimentation models and to apply non-deterministic analysis and regenerative transient analysis. With this paper, we realize a compositional approach that enables quantitative evaluation of well-nested and complex workflows, that decomposes the workflow based on its topology, analyzes identified blocks in isolation, and recombines intermediate results numerically. We also provided a class of distributions that enables the approximation of histograms generated by real data. At the moment, we are investigating on how to extend the compositional approach to structures that exhibit non-well-nested patterns, such as replicated events or repetition and loops. Thank you.